In this video, we're going to talk about how heat or thermal energy is used in phase changes. And so there are 6 different phase changes, 5 of which are included on your chart. I forgot to include changing from a gas directly into a solid. And these phase changes have particular names that go with them, how the heat is going to flow, and whether or not that will be endo or exothermic. And so when you change from a solid to a liquid, that is called melting, which you should be familiar with all of the phase change names. When you reverse that and go from a liquid to a solid, that is called freezing. When you change from liquid to a gas, that is called vaporization. And one little side note about vaporization, that can include both boiling and evaporation. However, evaporation, it doesn't actually have to be at a particular temperature for it to evaporate, but in order for it to boil, it does. Evaporation happens at the surface of the liquid, whereas boiling happens throughout the entire liquid. Now, reversing vaporization, going from a gas back to a liquid, is called condensation, which we see on our soda cups or our drinks at restaurants, how they get the water on the outside of the glass. That's because the heat from the air is going into our drink, and that water vapor that is in the air is cooling down and condensing on the side of your glass. When you change directly from a solid to a gas and you skip the liquid phase, that is called sublimation. And we looked at dry ice in class, and so you saw that when dry ice, which is solid carbon dioxide, was on the counter, it was going, you could see smoke coming off of it. That was the dry ice going directly from the solid to the gas phase. It was not getting liquid everywhere. And the reverse of sublimation, so going from a gas directly into a solid, is called deposition. I like to think of it as the first part of the word is deposit. So like you're depositing a solid somewhere, you're setting something down. I don't know, it just kind of helps me. But I remember that sublimation starts out as a solid because both solid and sublimation start with an S. So hopefully that will help you. So for direction of flow, okay, we want to talk about is heat being absorbed or released? Is it going in or out of our system? And so heat, in order for it to melt, heat has to flow into the system. So it's flowing into or it's being absorbed, okay, which means that's an endothermic reaction. It's going to start to feel warmer. And so the other phases that do that are vaporization, which is absorbing heat in order to change from the liquid to a gas phase, as well as from sublimation is going into or being absorbed. It is an endothermic process. Now, something I mentioned this last column, delta H. H stands for, that capital H stands for enthalpy, which is the bond energies, or the energy required to break the bonds. So delta H means change in enthalpy. So that triangle equals, it's the Greek letter delta, and it means change in. And so that means the energy required to break the bonds. And there are different values, whether or not it's a solid, liquid, or gas, or what phase change is going on. But for melting, we use our delta H of fusion is what we call it. And that word fusion is just a label telling you which delta H we're referring to. And this delta H is going to be a positive value because we're absorbing heat. And so for vaporization, we call it delta H of vape. That way we don't write vaporization. It would be a very long word. And that will also be positive. And again, our delta H of, actually, I don't know, maybe it's sub for sublimation, but it will also be positive. Now, when we look at the other processes, okay, freezing, for example, heat flow is going out of. So it's flowing out, which means it's being released. And I'm drawing it in blue because it means whatever is freezing is going to start to feel colder because there is less heat. Okay, and so that means it is exothermic, and that means our delta H of fusion, okay, it's still that same value, but instead this number will be negative. Positive and negative just shows the direction, not higher or lower than 0. Okay, so positive or negative is just our direction. And so the same can be said for condensation, okay? But instead of delta H of fusion, again, we're doing delta H of vaporization, but it's the opposite. It's negative instead of positive, but it's literally the exact same number, which we saw in our warm-up on April the 15th, which was today. So you can check out some of your warm-ups to see examples about that. But that means deposition is also heat is being released or flowing out of the system, which makes it exothermic. And so our delta H of sublimation would be the negative version of that number. And so what this all tells us is that in all the phase changes, the energy or the heat is being used to break intermolecular, well, break or form, depending on whether or not you're heating up or slowing down, but it's using to break or form those intermolecular forces that are between the bonds that we talked about in our phases. So it's used to break intermolecular forces in endothermic reactions or form those intermolecular forces in exothermic reactions. But the key thing is it is not being used to break bonds. It is not breaking bonds, and therefore there is no chemical change. Here there's no chemical change, and this means that phase changes are physical change. They're a physical change. So if you look at water as a liquid, changing to water as a solid, we call that process freezing. But because it stays H2O as reactants and products, we know it's a physical change. Nothing else is happening there. It also means that there's not really a temperature change either, because if the heat is being used to break or form those forces, that means it's not being used to speed up those bonds. And so one way we look at phase changes is through a phase change diagram. And so we looked at a cartoon in order to label these points, but on this video we're just going to kind of label them together. So where point A is, this is where you can find solids. And so a phase change diagram is just going to show how pressure and temperature interact. So if you have a very low temperature, remember low temperatures are going to be on the left, high temperatures are going to be on the right, low pressures are on the bottom, high pressures are at the top. So if you have a relatively low temperature and a semi-high pressure, you're going to get solid versions of whatever chemical it is that you are looking at. And so, oops, wrote that on line B instead of on line A. So this would be a solid, okay? Now, where point G is, this middle section, that's a liquid. That's where you still have a decent amount of pressure, but your temperature is hotter. There's more speed, so some of the forces have been broken. And so point E, which is between our solid and liquid, represents that whole line. Any of those points along there are different E values. And that is just, if you're going from a solid to a liquid, you're heating up, then E represents melting. But if you're cooling down, then E represents freezing. So it's just a graphical way of representing what we just talked about. So melting and freezing are the phase changes that are occurring between a solid and a liquid. Now, point F is between liquid and something else. Well, the only other phase there is gases. So F represents when you go from a liquid to a gas, you have vaporization, but the reverse of that is condensation, which is going from a gas to a liquid. So point F is vaporization and condensation. Now, point C is in between solid and gas, and so point C is going to represent sublimation, which again, sublimation starts with S, so it starts out as a solid, and then deposition is when you go from a gas to a solid. And so we'll just record that both on our graph and off to the side here. And those two are the phase changes that you're most likely the least familiar with. And so point B and point D are special. So point B is the triple point. And the triple point is special because you can see all three phases of matter at the same time. So all three phases or states of matter at the same time, which is key because when you're melting, you see solid and liquid. When you're boiling, you see liquid and gas, but you don't normally see a solid, liquid, and gas version of the same chemical at the same time. And so D represents the critical point. Now, the critical point is interesting because liquids and gases are very similar in the fact that they both flow. If you look at the way they move, they both flow. But at the critical point, anything with a higher temperature and a higher pressure from that point is in what we call its own little phase. It's called a supercritical fluid. We use fluid because we know gases and liquids still flow, but the crucial thing about it is you can no longer tell the difference between a liquid and a gas. It's this special fluid that we just, it's used in, NASA uses it for their GPS systems for rockets and satellites and things like that. So it's pretty cool, but I don't know a whole lot about it beyond that. So if you're interested or intrigued by that, you'll need to go on the internet and do some research and find out what Google will tell you. So yeah, so that is phase changes.